All right, welcome back to Math 098. We are actually ready to get into word problems. So we set up our understanding of substitution method, elimination methods for solving systems of equations. I know we did start with graphing, but for solving word problems with multiple variables, we're probably almost never going to graph. So we need to really hone our skills for substitution and elimination methods. So having said that, we are ready to move into our first type of word problems for this unit, and that is motion problems, or in other words, distance problems. As a reminder, recall that distance is equal to rate times time, so we're going to use that as a guide. Now, I'm a very visual person. I know a lot of my students tend to be very visual people. So I like charts, right? I like charts. I like having a graphic organizer so I can put all my information exactly where it belongs, and then I can pull my equations from that particular graphic organizer. I think once you see this setup, you'll like it very much. Consider distance tends to be the trickier of the bunch, and you'll see we're going to touch on interest, we're going to touch on mixture problems, and then some miscellaneous problems. So bear with me. It might be a little bit tricky at first, but hopefully it starts to make sense to you, and you're getting a sense of, okay, so we have a few things going on here. Let's try to figure out where I am in terms of like different scenarios, things like that. I know that doesn't mean anything right now, but it will in just a second. So let's take a look at our notes. We left off on page 10. We are ready for motion problems. Okay. So for this particular section, we may or may not need systems of equations. So it really just depends on the information that we're given. And I'll break that down as we move along. First off, your graphic organizer. So here it is. Here's your graphic organizer. Notice you have player 1, player 2. I mean, that could be train A, train B, car A, car B. It could be John and, Bobby or something. Whatever the names are, who cares, right? So your characters go here. And then what I like doing is I like using these column headers, so rate, time, distance. Also notice I embedded the formula here. So rate times time is equal to distance. Now, if you're not provided distance and you're provided the rate and the time, then the distance is simply rate times time. So rate times time goes here. Rate times time goes here. Think about what each of these cells mean. So this first cell right here represents the rate of player 1. This cell right here represents the rate of player 2. This cell here represents the time of player 1. This cell here represents the time of player 2. And then finally, this cell represents the distance of player 1, and this cell represents the distance of player 2. That is how we interpret our graphic organizer. Now, no problem, Noelia, and thank you for that work. That's actually perfect. Now, in terms of setting up the distance equations, we have 3 scenarios here that we're going to consider. So our first scenario is where we add up the distances and it's equal to total distance. An example of where you would add up the distances. All right, so let's imagine that you have person A on this end and person B on this end, and they're working together to meet, right? So they work from opposite ends and they come towards each other and they meet. Now, they may not meet in the center. It's possible that maybe one is faster than the other, right? So they might meet like not quite in the center. But the bottom line is whatever distance this person 1 covers and whatever distance this person 2 covers, the sum of their distances will be that total distance that separates them. Let's say this were 10 miles. And let's say that person 1 covers 6 miles. That means person 2 covers 4 miles, right? Because it's 10 total. That's scenario 1, where you'll add up the distances and set it equal to total distance. Okay. Scenario 2. Notice here for scenario 2, this says distance 1 minus distance 2 is equal to the distance separating 1 and 2. An example of this is a race, right? Let's say you and I are in a race and we're running, right? We start at the same time. We're going in the same direction. So nobody's, playing games. Nobody's taking a shortcut, right? We're in a race. We start at the same time. We're going in the same direction. we're running. And because my knees are all busted, they're terrible, I'm not good at running, I go, but very slowly, right? So I'm, trekking my way, but you're flying past me. So at some point, you're so far ahead of me, but I'm like, this far. So we start at the same point. You're so far ahead of me, right? So what we end up doing is we say, well, okay, so if I know that one person's way faster than the other one, well, how long before they are X miles apart, right? So essentially what we would do is we would say, okay, well, the distance of person one is here, the distance of person two, me being the slower one, is here, and then this distance that separates them, well, we can easily find that by subtracting, right? If you run 5 miles and I only run 3 miles, well, then there's 2 miles that separates us, right? And that's because we would subtract our distances. So when you think of scenario 2, think of like being in a race, okay? In a race, meaning you start at the same location, you're going in the same direction, and you start at the same time, okay? That is incredibly important to keep in mind. Hi, Patrick. Good morning. Now, if you take a look, scenario 3 says distance 1 is equal to distance 2. Now, the case for when this would actually happen is, let's say I knew I was going to be very, very slow, right? And I'm like, Patrick, let's go for a run, but I'm going to get a 30-minute head start. I'm sorry. I'm just going to start off because I know that you're super, super fast. And we plan on running for like 2 hours. Who does that? But anyways, so I go to the specified location and I'm off. And I'm running for 30 minutes. And then Patrick says, okay, it's my turn to start running. So he shows up at that location 30 minutes later and he books it. He's like, oh yeah, I'm going to catch up. I'm going to catch up. And surely enough, even though I'm, trekking away, after a certain amount of time, all of a sudden it's like, whoa, there he is, right? So Patrick catches up. So typically, when you see this particular scenario where the first distance equals that second distance, meaning they cover the exact same length here, and actually I'll show it this way. Start at the same location, one person's going, and then the other person catches up, right? So if they catch up, your distances are equal. Typically that'll happen if one person or the character, one character is starting earlier than the other one. So that's something to consider, okay? And then the second person will catch up. Think of it like that. So that second character is going to catch up to the first. So very quickly, I just want to take a couple notes, put that on the side, so that way it's very clear to you what it is that we just broke down together. So for distance 1, imagine here that you have A and B on opposite ends, and then they work towards each other. So they're essentially working towards each other, and then this is total distance. This is scenario 1. Actually, another example of this is, what if they start at the same location, right? A and then B, but let's say they go in opposite directions. So let's say A goes to the east and B goes west. And then at this point, we're now going to add up their total distances. So it's still a sum. So there's actually two different cases for scenario 1. I always find drawing diagrams is really helpful. I hope you all agree with that. Okay, perfect. Now for scenario 2, I want you to think of people in a race. So scenario 2, we'll say 2 characters racing. Okay, so when you think of 2 characters racing, I want you to think same location, same time, same direction. Same location, same time, same direction. Okay, now with scenario 3, I want you to think of one character catches up to the other. Okay, for scenario 3, one character catches up to the other. So essentially, it would probably be the exact same starting location, but one person will have a head start. So meaning the times are not going to be the same, right? The time that one person travels will not be the same as the time that the second person travels, because one of the two is going to catch up to the other. All right. Hopefully the visual helps the ideas that I was trying to paint. I'm hopeful that you can visualize it. Let's try this out. So we're going to set up the chart and solve. So we're setting up this motion problem chart for each of our following word problem examples. Car A travels at a rate of 50 miles per hour and car B travels at a rate of 45 miles per hour. If both cars leave the same location at the same time, traveling in the same direction, how long will it take before the cars are 25 miles apart? Thinking about this scenario, right? Same location, same time, same direction. We know that this has to be scenario 2. The two characters are racing. In this case, it's car A and car B. So we're going to say scenario 2. Cars are essentially racing each other, right? We know that because it's the same location, same time, same direction. So let's set up our chart. So we have rate, time, distance. I apologize for moving this. I just want this to be easier to write out. And then we have car A and car B. All right, let's input the given information. You're told that car A travels at a rate of 50 miles per hour. So I'm going to put a check mark over 50. And I know that the rate of car A belongs in this spot right here. So we're going to write 50. If you would like, if you find it helpful, above rate, we can write mph so that it's miles per hour, which means that the time is in hours and the distance is in miles because it's miles per hour. I think that's a really good habit to get into so that you know your units of measurement. We're also told that car B travels at a rate of 45 miles per hour. So let's go ahead and input that in the chart. Now, those are the only values we're actually given outside of the fact that they're 25 miles apart from each other. So check this out. Both cars leave the same location at the same time. We are not told any information about how long it takes, right? Even the question says, how long will it take? So in which case, if we know that they're the same time, but we don't know how long it'll take, that means they're both the same variable. We do not need different variables here because they have the same time. And in math, same means equal. So in this particular problem, it does not say how far car A travels by itself. So we cannot put a value here for distance. We also are not told how far car B travels. Otherwise, that would be here in this spot. What we do know is that they will be 25 miles apart from each other. So to finish this chart, recall that rate times time is distance. So 50 times t is simply 50t. And then for car B, 45 times t is 45t. Now look at the formula for scenario 2. It says distance 1 minus distance 2 is equal to the distance separating them. Okay? So distance 1 minus distance 2 is equal to the distance separating 1 and 2. Quick question, does it make sense to have negative distance? Can you say, oh, the answer is -5 miles? No. When you think about this and you're writing your equations, just be logical. You're going to put the faster person first, right? So for instance, here we have 50t and 45t. You're going to write 50t first. 50t minus 45t. it doesn't make sense to do reverse because then you're going to have negative distance. And we're not going to have negative distance because that doesn't make sense. Like, what does a negative 5 miles look like, right? Like, that's just weird. So be super logical as you write your equations. If it doesn't make sense, don't write it. Think of a different perspective, okay? Don't write things that don't make sense. Please, 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 okay? So setting up our chart, the faster person, or the faster car in this case, that's 50t, minus the distance of the second car, the slower car is 45t, is equal to the distance that separates them. Now the cool thing is the word problem itself tells us how far apart they are from each other, and they are 25 miles apart. All we have to do at this point is solve, so we're going to combine like terms. 50t minus 45t is 5t, is equal to 25. And then we're going to divide both sides by 5, because again, we want to isolate t. 25 divided by 5 is 5. Now, it is not enough to simply say t is equal to 5, because we need units. Now, if you're ever unsure, go back to your chart. T, where's t? Where's t? Ah, t is here for the time that it takes car A to travel and the time that it takes car B to travel. And notice that t is in terms of time, which is hours. See how all of the information is here for you? You just have to go back to the chart. So t represents time, which is in hours. So t is 5 hours. The question is, how long will it take before the cars are 25 miles apart? Well, there's our answer. It will take 5 hours before the cars are 25 miles apart. Okay, so essentially, there's your answer. Okay, it will take 5 hours before the cars are 25 miles apart from each other. Now, sure, that's awesome. But what if I wanted more information? What if I wanted to know how far car A traveled or how far car B traveled? So let's do a little side quest here. Side quest, because I'm a nerd and I'm a gamer and I like it. So let's talk side quest. I want to know the distance of car A, and I also want to know the distance of car B. Well, if that's the case, again, go back to the chart. The distance for car A is represented as 50t, right? It's right here in the chart. The distance for car A is 50t. And the distance for car B is 45t. Well, guess what? You know what t is. T is 5. So this is going to be 50 times 5, which is 250. Remember, distance is miles, so 250 miles. That's how far car A traveled. For car B, we'll do 45 times 5, which is 225 miles. If you do the math, you can verify that it is, in fact, 225 miles. Okay? Kayla, be very careful with your units. T represents time, not the rate. So now, notice we found the distance that car A traveled, which was 250 miles. We found the distance that car B traveled, which is 225 miles. How many miles separates them? Oh yeah, 25. Okay, so by investigating a little bit deeper, we can actually verify that all of this work is perfect and it all checks out. As always, if you have any questions, please throw them into the chat. I'll be happy to answer those. I know these get a little bit tricky. For right now, bear with me because we've only seen scenario 1. We still have to see the other scenarios as well. And I hope that it makes sense as you kind of unveil each of these different types. Let's take a look at problem number 2. 2 highway paving crews are 20 miles apart working towards each other. This is incredibly important. They are working towards each other. Without even reading anything else, we know which scenario this is. The two crews are working towards each other. So we are actually referring to scenario 1, okay? So I'm going to make a note of that this is scenario 1. I'll even write down the formula too so that we have it. So because this is scenario 1, we're going to say distance 1 plus distance 2 is equal to total distance. Okay, let's keep reading. One crew paves 0.4 mile of road per day more than the other crew, and the two crews meet after 10 days. So find the rate at which each crew paves the road. So ultimately, our goal is to find the rate. So let's set up our chart. We have rate, time, distance. I apologize for having to turn the page again. So rate, time, distance. We have two crews. No, that's okay, Kayla, seriously. We have two crews, so I'm just going to call this crew 1 and crew 2, if that's okay. Crew 1 and crew 2. All right. Two highway paving crews are 20 miles apart. So they are 20 miles apart from each other. If it helps, we essentially know that that's total distance. Okay, the total distance is 20 because they're 20 miles apart from each other. Good. Now, one crew paves 0.4 mile of road per day more than the other crew. 0.4 mile of road per day, that's a rate. More than, that means plus, the other crew, which is unknown. So check this out. We're in the rate for crew 1. So crew 1 paves 0.4 mile of road per day more than the other crew. That means we don't know the other crew. So I'm going to write that as C. If it helps, we're going to write miles per day, which means time is in days and distance is in miles. 0.4 mile of road per day more than the other crew. We know more than means addition, so that actually ended up being an expression, which is kind of crazy. We're then told that the two crews meet after 10 days. So they both meet after 10 days, meaning they both work for 10 days. So the time here is going to be 10. All right. So we have to find the rate at which each crew paves the road, but we actually did not finish our chart. So we have two spots that are still missing. Well, that's simple. We know that the formula for distance is rate times time. So for crew 1, the distance is going to be rate times time. Now here's how I would like you to write this. 0.4 plus C is the pair of terms. So you always package the pair of terms in parentheses. And it's rate times time, so I'm going to put the 10 in front. So it's 10 times, parentheses, 0.4 plus C. And then for crew 2, the distance is going to be rate times time, which is 10C. Excellent. Now that we have our chart completely filled in, well, we already have a formula. Distance 1 plus distance 2. Okay, so distance 1 is 10 times 0.4 plus C plus, and then distance 2 is 10C is equal to 20. How cool is that, right? You already have the framework, so all you're doing is substituting these values. Obviously, the chart is probably going to be the trickiest piece to this, but once you recognize which scenario you're talking about, you'll make the substitution, and then you're just going to go through the motions of solving. So we're applying our techniques that we learned way back in Unit 2. So 10 times 0.4 is simply 4, plus 10 times C, which is 10C. Then we have plus 10C is equal to 20. We are going to combine like terms first, 10C plus 10C. So we have 4 plus 20C is equal to 20. My like terms are 4 and 20, but they're on opposite sides, so I'm going to bring the 4 over to the 20 so that I can isolate my 20c, or the term of the variable. So I use the opposite operation to move to the opposite side. 0 plus 20c is 20c. 20 minus 4 is 16. Divide both sides by 20, and you get that c is equal to 16 divided by 20. Now, because our original problem starts with a decimal, we can have decimals as answers. So c is equal to 0.8. All right, 0.8 what? So let's go back to the chart and find out where c is all by itself. So if you look through, you look through, you look through, and you say, oh, here it is. C is alone in the rate for crew 2, and the rate is miles per day. Ah, okay. So crew 2 has a rate of c miles per day. So we're going to write crew 2 is 0.8 miles per day. That takes care of crew 2. Now, we are not finished because we're asked to find the rate at which each crew paves the road. So we still need to figure out crew 1. If you go back to the chart, notice here we have 0.4 plus c is the rate for crew 1, which means crew 1 is a little bit faster than crew 2, right? So crew 1 is going to be 0.4 plus c, which is 0.8, and that's going to be 1.2 miles per day. And that represents the solution to this problem. So let's go ahead and identify that. Okay? We've successfully answered the question being asked. Find the rate at which each crew paves the road. What I'd like you to do in the chat is to tell me how far each crew went, meaning how many miles of road did each crew pave? I would like you to answer that in the chat. Go for it. Excellent. So Noelia says that if you consider looking at the chart and you want to find, this is our little side quest here. You want to find how far each crew went, or how many miles of road did each crew pave? Well, if you take a look at crew 1, the distance is 10 times 0.4 plus c, and we know that c is 0.8. So essentially it's 10 times 1.2, which is 12 miles. Okay, excellent, Patrick. Make sure you always use units, by the way, for everything that we do. So 12 and 8 true, make sure you write down miles. So for crew 2, we have 10 times c, and c is 0.8, which is 8 miles. So again, this is just a little bit of side information, but I just want you to see what you're able to do with that particular chart. Okay, so far we saw scenario 2, where both of the cars were racing, and scenario 1, where they're working towards each other, so it's total distance. Let's take a look at number 3. Train A leaves the station traveling at 32 kilometers per hour. 2 hours later, train B leaves the same station traveling in the same direction at 52 kilometers per hour. How long does it take train B to catch up to train A? What do you know? Scenario 3, right? So I'm going to write here that scenario 3 implies that the distance of the first one is equal to the distance of the second. Cool, right? We have a framework. All we have to do is make a substitution. But obviously, the first thing we need is a graphic organizer. So let's set up our chart. Rate, time, distance. Okay. We have 2 trains. We're going to call it train A, train B. Perfect. Train A leaves the station traveling at 32 kilometers per hour. So 32, and then I'm going to write above it kilometers per hour. which implies that time is in hours and that distance is in kilometers. Okay? It's always helpful to make note of what those units of measurement are. 2 hours later, we're going to hold on to that note. Train B leaves the same station traveling in the same direction at 52 kilometers per hour. All right, now let's deal with this whole 2 hours later business. Okay, let's think about this logically. Train A starts to go. Okay, train A is going, train A is going. 2 hours later, train B is like, oh, snap, I gotta go. Train B is off, and then eventually train B catches up to train A. So thinking about this logically, and thinking about how long each of these trains have been traveling, we can safely say that no matter what, train A was traveling 2 hours longer than train B, right? That is safe to say that train A has traveled 2 hours longer than train B. So having said that, look at what we're going to put in the chart. Train A, for a fact, we know train A traveled 2 hours longer than train B, which means the time it took train B is unknown. That's our B variable, okay? This concept you may have to hear a couple times, but think about it logically. Train A goes for 2 hours and then train B starts. So train A was definitely traveling for 2 hours longer than train B. Some of you may want to say, well, doesn't that just mean that train B was traveling 2 hours less? Yeah, sure. But honestly, I like dealing with positives. I like keeping most of our values positive whenever we can. So I am simply going to say train A was traveling 2 hours longer than plus train B. So 2 plus B. Okay? Distance. The distance for train A is rate times time. 32 times 2 plus B. The distance for train B is rate times time. 52B. Now, according to our scenario, which is scenario 3, the distances will be equal to each other. So the distance of train A is equal to the distance of train B. Let's solve. 32 times 2 is 64. 32 times B is 32B. At this point, notice my like terms, so I want both of these to be on the same side. So I'm actually going to bring over the 32B by subtracting it. That leaves me with 64 is equal to 20B. And then I'm going to divide both sides by 20. So we find that we have 64 divided by 20, which gives us 3.2. Now I know for this particular problem, you weren't given any decimals to begin with. I want to write my answer as a decimal because we're talking about time. We're talking about units of measurement, which are continuous, so 3.2 makes sense. So how long does it take train B to catch up to train A? Well, B refers to the time train B took, and time is in hours in this case. So we're going to say 3.2 hours. So it took train B 3.2 hours to catch up to train A. And there's your solution. Good. Take a moment and tell me how far train A traveled and how far train B traveled. So again, this is our side quest. And I want to know, what's the distance of train A and what's the distance of train B? Take a moment, put that in the chat. Perfect. So Ryan concludes that it actually ends up being 166.4 miles for each of them. But that should make sense, right? Yes, perfect, Noelia. Their distances should be the same because train A is off to the races and train B catches up. Okay, so we can write here, this is 32 times 2 plus, and then B in this case is 3.2, which ends up being 166.4 kilometers. Perfect. And then train B is 52 times B, which is 3.2. And again, that's also 166.4 kilometers. Very, very nice. In this case, our distance is in terms of kilometers. So perfect. Thank you, Rachel, Patrick, Ryan, Noelia. Beautiful work. Let's turn the page and do another problem. And actually, what I'd like you to do is I want you to try number 4 on your own. Think about which scenario we're pertaining to. Go ahead and fill in your graphic organizer and solve this problem carefully. I'm going to give you only 4 minutes to do this problem. As soon as you have answers, go ahead and type them into the chat. But you have 4 minutes. Give this your best shot, okay? I want all of you to try this, starting now. Okay, let's take a look. So a motorcycle traveling at 60 miles per hour, so we have 60 miles per hour, which implies time is in hours and distance is in miles. Overtakes a car, this is the same as catches up, which is like ding, ding, ding. We know exactly which scenario we're referring to. So overtakes a car traveling 30 miles per hour. So there's the rate of my car. Now the car had a 3-hour head start. So how far from the starting point are the two vehicles? Okay, so catches up implies scenario 3. So that's the first thing I'm going to write down here with regards to the equation. So scenario 3 implies distance 1 is equal to distance 2. Now we are told that the car had a 3-hour head start. So I want you to visualize. The car starts at a specific location and travels for 3 hours. Suddenly, the motorcycle appears at that starting point and then floors it, right? They're going twice as fast. So they floor it and they catch up to that car that was going pretty darn slow. Okay, so the car had a 3-hour head start, which means that the car was traveling for 3 hours longer than the motorcycle. So in which case, the time it took the motorcycle is simply m. Now, the distance of the car is 30 times 3 plus m. Perfect, Noelia. Keep going with that. You have one of the pieces of information. Now, the question is how far from the starting point are the two vehicles? So we want to know distance. For the motorcycle, the distance is 60 times m. We're now ready to apply our formula, our framework. So the distance for the car is 30 times 3 plus m. The distance of the motorcycle is 60 times m. At this point, we're going to distribute and solve. So that gives us 90 plus 30m is equal to 60m. Notice my like terms. We want them to be on the same side, so we're going to bring over the 30m. That leaves us with 90 is equal to 30m. Divide both sides by 30, and you get that m is 3. But 3 what, right? So in the chat, Noelia pointed out that this 3 refers to time, which is hours. She's completely correct. Take a look at the chart. Yes, thank you, Noelia. So m is the time it takes for the motorcycle to catch up, and time is in hours. So 3 hours is the time it takes the motorcycle. Now here's the big thing. That's not what we're being asked. We're being asked how far from the starting point are the two vehicles. So that whole thing about the side quest, that comes into play right now. So the distance for the car and for the motorcycle are what's going to answer this question. So the car traveled 30 times 3 plus m. M is 3 hours. So it's going to be 30 times 6, right? 3 plus 3 is 6. 30 times 6 is 180. And then let's look at distance. Distance is in terms of miles. Let's look at the motorcycle. The distance of the motorcycle is 60 times m. Thank you, Rachel. And m is 3, so the motorcycle is also 180 miles. And that actually represents the solution to this problem. Beautiful work on that one. We looked at distance problems that dealt with one variable. So on Monday's class, or for our next class, we're going to look at distance problems that involve two variables. All right, wonderful work today. I will see you all on Monday. Have a fantastic weekend. Make sure you're practicing these problems. See you on Monday. Bye.